Okay, this is the sequel to the previous video I made where I showed you how to design a vise jaw for your vise. And in this case, I designed a vise jaw for a 4-inch Tormac vise. So, next I'm going to show you how to do the toolpaths and post the G-code for this. So, let's see, there's a couple things since the last video that I want to change. So, modify, I'm going to go into change parameters and check the dimensions in here. So I changed the width to 4.5 inches. The height is 1.5 and the thickness is 0.75. And since I made that video, I also bought some material, and my material is 0.75 thick and 1.5 wide. So the problem with that I realized after the fact is you always need some material at the bottom to hold onto to machine your part. So that leaves me really no material to hold onto while I machine this part. So I decided rather than try to make this thinner, I don't really want it to be thinner because I want to maintain rigidity and make sure I have some material to cut into later. So rather than make it thinner, I decided it'd probably be best to just eliminate these corner radiuses, leave a saw cut at the ends, and then just make it not quite so pretty and perfect looking. So it'll be rough saw cuts. It's going to be rough extruded material on the top. And later I can always mill that down flat while it's on the vise. So I'm not too worried about that. So what I'm going to do here is I'm going to back up my history timeline to get rid of both those things. And then I'm just going to add a chamfer. So I'll add it back to these edges. And then 1, 2, 3, where is that? 4 edges. And you can make that 0.02. So that should work. So I'll still face this surface and the back side just so they're parallel to each other. I'll hit save, and I'm going to go into manufacture workspace. So I already have a setup here, but I'm just going to create a new setup to start this from scratch. So you can immediately see my Z is pointed down and I want my Z pointed up. So it's pointed down because that's the direction that the model was built in. But I'm going to change it. Instead of model orientation, select Z plane and X axis. So this is purely for the direction, the orientation of the axes, not the location. So I selected the face to make Z up, and then I'm not even going to select anything for X. I'm just going to flip my X axis so it's the way I want it. Next, we have origin, and I'm going to, on this, I put a lot of thought into whether I should do model box point or stock box point, and that's basically either this point, which is the corner of the stock, or if I do model box point, it's the corner of the finished part. So on this one, I'm actually not too worried about it because I'm just going to say the stock is the size of the model. Now the finished part is going to be slightly thinner than 0.75 because I need to have just a little bit of material to face off. So I'm thinking it's probably going to be 10 thousandths on either side that I can, might have to be a little bit more than that to get a fully clean face, but I'm going to try 10 thousandths. But that does not affect how we model this or how we machine it or how we do the toolpaths, but it will affect how we run it in the machine. So that's to worry about later. So I guess I'll keep it relative size box, no additional stock. So the stock is the exact size of the model, which is these numbers here. Hit OK. Hit save. And as you can see, I'm on setup 3. I've messed with this a little bit. So the first thing I want to do is face the top. And I'm working with a Tormac cnc 440. If you're not familiar with that machine, it's got about the same footprint as a refrigerator. So it's a really small machine. The nice thing about it is it goes up to 10,000 RPM. So for a small cutter, which is what I'm mostly using, I can still move pretty quickly through material. So normally for facing, I'd want to use the biggest end mill possible. But for now, I'm just going to grab this 1/4 inch. Normally I would use the 3/8, but just since I happen to know that the 3/8 is not going to fit very well down in this bottom hole, I'm just going to see how the 1/4 inch does and check out how much time it takes. I'm not as worried about time as I am about convenience and having a good part. Another factor, this is totally something about my machine, but I don't have an automatic tool changer, so I'm doing manual tool changes. So if I can save myself a tool change, that's kind of nice, especially if I want to run several of these. So geometry, if I don't select anything, it defaults to the entire stock model, so I'm just going to leave that. Heights, the bottom height is the lowest my tool is going to go. The top height is where the material starts, so I'm going to leave both of these where they are. Even though the stock top is the model top, I'll take care of this. When I touch off the tool in the machine, I'm just going to subtract 10 thousandths and make sure that pass has enough material to clean up leave a clean machined face. Passes. Okay, this step over is good. So the step over, I want to make sure that's less than my tool diameter. So it is, because I'm using a 1/4 inch. Again, you might think I'm crazy for using a 1/4 inch to face a part like this, but it is a pretty small part. Let's see. I think everything else is good. Oh, I like to hit this extend before retract. And that extend before retract just is here. It makes sure, if that's not clicked, it'll lift right when it gets to this point. So I want it to fully leave the part before it retracts up. That looks pretty good. One other thing, I'm going to go back in and edit this. I'm just going to do this pass extension. I'm going to do 0.25 just in case I cut my material a little oversized. I'm not going to do this super precisely, so if my material is just a little oversized, I don't want it to come down and plunge into the material. So I don't anticipate it's going to be this much oversized, but that little bit of feed move is not going to add too much to my time. So that worked there. Save. And now I'm going to use 2D adaptive clearing. So 2D adaptive clearing and 2D pocket are both roughing toolpaths. And whenever possible, I use adaptive clearing because it gives you a much smoother toolpath. It lets you go full depth, and it guarantees that you're not going to exceed your maximum step over. So alternatively, Pocket is very similar, except sometimes the tool will go full with the cut into material. It's not as concerned about maintaining a consistent step over. So 2D Pocket, you have to be careful. You could break your tool if you're not careful how you use it. 2D Adaptive, you can be a little bit more careless and know that your tool is not going to break as long as you're putting in reasonable numbers. So there's also 3D Adaptive and Pocket. Anytime you have a really simple geometry like I do, as far as vertical walls and a flat bottom, it's better to use 2D. It's just going to behave more predictably. So I could use a 3D adaptive, but it's going to be trying to look at other stuff that I don't really need to worry about for this simple of a pocket. So again, same tool. All my speeds and feeds are based on the machine I have. So 10,000 RPMs. This will all depend on your machine, but if you have 10,000 RPMs, you might want to you should use that for a 1/4 inch carbide end mill. Okay, pocket geometry. So I'm going to select, let's see, if I select these bottom areas, I think that will work. Heights. So the important one here is bottom height. So from selected contours, so that's where I selected down here, offset 0 inches. So that's how deep I want my tool to go, which is correct. Height, usually stock top is good for most simple stuff. So that's where the, you're telling it where the material starts as you're coming down in Z is the top height. And then retract and clearance both should be above that. Stock to leave. Normally when I'm roughing, I want to come back and do a finishing pass. For this one, I'm going to try to just leave that off. So sometimes that will give me some imperfections in the walls here, but I'm not really concerned with having perfect walls in here. So I'm just going to try it out, leave that off. So the important number here is optimal load. So you can think of this as, you might want like a percentage of your tool diameter. So I've seen some people will say they use like 50% tool diameter, some people 25% diameter. I'm going to go a little conservative here. Let's see, 1/4 inch end mill. So what's 10% is 25 thousandths. I'm just going to do 0.03. No, I can do more than that. I'll do 0.05 and see how that goes. So that's what, 20%, right? Yeah, 20%. And again, I don't need to do multiple depths. On a more traditional roughing toolpath, I would do multiple depths, but with adaptive, I feel comfortable that I can go full depth. And this optimal load is my radial engagement, my maximum radial engagement. So I know it won't exceed that, so I can safely go full depth. Okay. And I think everything else in here is good. I'm going to leave that. Okay, and this did not do exactly what I wanted it to do, and I think I know why. So I was expecting this to do a helix down to the bottom. And I think the reason it didn't is because of the geometry I selected. I selected this surface, and I think it thinks, based on that there is no material in here. So I'm going to go in, I think if I double click here, yeah. Reselect my geometry. I'm going to do this edge rather than that surface. Rather than this surface, I'm just going to do the edge, and hopefully that picks up everything inside that edge. So here we go. And yes, that did. So it does a helical entry all the way to the bottom, which is the best way to plunge. You don't want to just take the end mill and use it like a drill and go straight in. That's harder on the end mill, even though it is possible. So save there. So that got me down to this surface. Now I need to break through down here. So again, normally I would always use adaptive clearing. Since I've tested this out before, I already know that adaptive clearing will not work because this helix diameter, even I could make a really tiny helix diameter, but to do a helix into this hole is difficult. So I found already that 2D Pocket does work well in this case, which usually I try to avoid the pocket, but I'll show you how this is going to work. So I'm going to select both these bottom edges. Again, that's the same tool, 1/4 inch. And bottom height is selected contours, so I'm good. I'm going to break through, so I'll do an offset of -0.03. Maybe I'll do -0.05 just to be safe. Okay, I'm going to turn off stock to leave because I don't want to leave any stock. If I was concerned with cosmetics, I would leave stock and come back and do a finishing pass with a contour. Okay, let's see, what else do I need in here? I think the important one is the ramp type. So ramp is how you're going to enter the part. And like I said, the helix, I've already seen that it doesn't work here. So I'm going to do profile. So profile just follows the edge, the shape, or aka the profile, and ramps down in Z as it's following that outer edge. So 2-degree ramping out, that's all good. I'm just going to see how this looks. And yes. Yeah, so I'm happy with that. Let's see, the one thing I'm noticing is this starts ramping at the top, and I've already cleared out all this material, so I'm going to go in and change that. So the top height, I'm going to change this to selection and click this space. And maybe just to be safe, I'm pretty sure I don't need to do this, but I'll say 0.02 offset from there. So I think it already has that vertical ramp in, so I really didn't need that extra offset. But and then if I look from the side, it does break through. That's important because I'm going to come back and face off the back side, and I want to make sure that has fully cleared through and there's no like paper thin edge there. Okay, so that's that. And then my last thing is the chamfers. So I'm going to go 2D. And on this one, you can see there's 2D chamfer here. And here's a secret in Fusion 360. Even though there's 2D chamfer here, and I'll show you real quick. 2D chamfer, it works. And it even says there's cutter comp here. But if you try this, at least the last time I've tried this, and I've seen other people mention the same thing, it doesn't put the code in your program. It doesn't put it in your G41 or G42. So even though you say I want wear compensation, you're not getting it. Hopefully they figure out how to fix that at some point. But instead, the alternate way is use 2D contour. So I'm going to select, I have a spot drill. So I'm going to use a, let's see, is this the one? So I'm going to use this 1/2 inch spot drill. So a spot drill, it's not an ideal chamfering tool, but it actually works pretty well. So if you don't want to have to buy an extra tool and you already have a spot drill, you can use it. And it will be recognized by the CAM software as a tool that can do chamfers. So geometry, I'm going to select this edge. Oh, not that edge. Okay, here's another learning lesson. You select an edge and it gives you more than what you wanted or a different chain than what you wanted. You can reselect that edge. And now I'm going to say it's an open contour instead of closed contour. Open contour. And I can select whatever edges I want to be part of that contour. And then once I got it, which I only have that one edge, I'm going to say accept. So I have that one edge. Now I'm going to select this edge, do the same thing, click it again, open contour, just the one, accept. And now I'll do these top edges. So make sure you're clicking the top edge of the contour in all these cases. And bottom height, just leave it at selected contours, that works. Okay, so now here's where the magic kind of happens. So since we're using a chamferable tool, this chamfer box pops up. So it seems to know that we want a chamfer. And if your chamfer is already modeled, you can actually use a chamfer width of 0, and it will give you the modeled chamfer size. So if you put a number in there, let's say I put 0.05 or something, it's going to do an additional 50 thousandths from what I already have of chamfer. So if the chamfer was not modeled, I would select that edge and say 20 thousandths. But it is modeled. I'm going to say 0. Chamfer tip offset, I like to use something close to, I want to be closer to the top of the tool, closer to the top, away from the tip, so I'm at a larger diameter where I'm actually cutting. So this is a 1/2 inch spot drill, so I'm going to do, on a 1/2 inch spot drill, the tip length is 0.25, so I'm going to do 0.2, and that should get me higher up on the cutting edge. Okay, one more thing. Compensation type, I'm going to do wear compensation. So if you're not familiar with wear compensation, that's where we're using very small numbers to offset our toolpath rather than the full radius or diameter of the tool. And I like to have compensation when I'm doing chamfers because sometimes, I mean, chamfers in general are usually a pretty cosmetic thing, and I like the ability to cut a smaller chamfer, look at it, see how it looks, and then maybe make it a little bit bigger. I kind of like the ability to modify it on the spot on the machine. And cutter compensation, wear compensation allows me to do that. Let's see, horizontal lead in. I'm going to do a little bit bigger. I'll do 0.25. And let's see, anything else in here? Yeah, I'm just going to leave all of this now. Okay, so I remember I selected all 4 of these as geometry, and it's not showing it on the inner ones. I have a warning here. That probably has to do with my horizontal lead-in radius. So let's make this 0.1. And I like to keep this vertical lead-in radius small, so I'll do 0.05 for that. See how that goes. Okay, so now I got my chamfers on all of those. So the one thing I'm thinking about is if I do slightly overcut the length of my material, this chamfer might kind of taper off. I could use 2 different chamfers and extend that, but let's see, how would I do that? Geometry, yeah, you could do a tangential extension. Let me just see what would happen if I did 0.25 here. Okay, yeah, that seems to work. So yeah, that's the solution right there, that tangential extension. I think it messed with these inner ones, but I think that's okay. So save. So that's all the toolpaths I want. I'm going to really quickly simulate those just to make sure it's doing what I think it should. I like to turn off toolpath, turn on stock, just so I can watch it clean it up. Okay, speed it up a little bit. Okay, so that looks good to me. I always like to look at my statistics, see how the machining time is. So it's 5 minutes. That's kind of long for a part like this, but again, I'm working on a very small hobbyist kind of machine. So in that case, I think that's fine. I'm not in a hurry. So I'll just say good to that. Okay, so last thing, if I want to post out my code, and here's another thing. I can use the same code to do the backside because it's the same facing pass and then the same chamfer. So actually there's only 2 of those chamfers. So I can modify this code for the backside. So I'm not going to do the full code again for the backside. So now you're wondering how to get the code out of the machine. There's two ways to do it. The quick way to do it is just right click on your setup and post-process. The reason that's not the better way to do it is because there's a bunch of... So if you're on a Windows machine, this stuff all looks a little different in these windows. But all this stuff that you might change in here, you'd have to do that every time you post this code. And in most cases, when I'm writing a program, I post 3 to 10 times until I get the code right, until I'm happy with it. And so I don't want to have to go to post process every time I'm like, oh, I messed up something, I want to change that really quick. I don't want to have to change all those defaults. So the better way to do it is go create NC program. Then you only change those defaults once. So I'll leave my program 1001. Okay, so I'm posting to my desktop. I want to change my post processor down here. So you can see there's a lot of them. I'm going to go to Tormac Path Pilot. And then let's see, what do I want to change in here? So I have all these options of things I can change. And I think all this is good for me. So depending on which post processor you pick, these properties are going to be different. But in general, I like to not use sequence numbers, so turn that off. And in most cases, the rest of the stuff is good for me, so I don't change it. And then you can double check your operations. It should be the ones you just did. I'm going to hit OK. And now I can right click on that, post process. And then if I click view NC code down here once it's done, it'll pop up. So if you're wondering how I got this colorization, this is what's it called? Visual Studio Code. If you click over here, there's several G-code highlighters. I use this NC G-code version 0.13.0. You search for that, install it, and then make sure that's active. Your code will look pretty like this. So that's my code. I can now put that in my CNC machine and run my part. And that's it.